Can you see my screen?
Yeah.
Yeah.
Yes.
Awesome. Awesome.
I didn't see the link for it though on the website just now.
Let me check real quick for you. Yeah. So it should be in the meetup for today for this Cassava Disease Classification, and it should be right here. I'll share it on Zoom as well. Cool. Okay, we're going to start then. Thank you everyone for joining. This is Deep Learning Adventures. If you're joining for other meetups, thank you for coming. And if you've never heard of us, we're a fun and engaging community where we use deep learning and AI to learn more about deep learning and the theory behind it, but also have hands-on coding sessions like we will have our first session today. My name is George, and I'm joined today by my great colleagues, Robert and David, who are co-organizers of this great community meetup. And we're so excited to have you today and talk a little bit about this interesting data set and interesting challenge of classifying disease in the cassava plant or the yucca plant. Before we get to the challenge, you can find us on Meetup. We have links on the Meetup. The link is Deep Learning Adventures. If you've never joined us or this is your first time, we covered a specialization from Coursera called Tensorflow in Practice. And we have recordings for that on YouTube as well under this bit.ly Deep Learning TF. We covered convolutional neural networks, NLP, time series forecasting. And we also have had a fun and engaging interview with Lawrence Moroney. And we also talked about the Tensorflow developer exam in case you're interested in taking that exam. I just wanted to recognize some of our other meetups that have posted this event. I apologize. One of them is the Bethesda AI meetup. They've cross-posted our event, and a lot of our community members are members of this meetup as well. And it's a fun and engaging meetup as well, where they usually have they host events they host speakers from other companies, and they talk about interesting interesting topics around AI and machine learning. The other two meetups that cross-posted this event was Data Education DC and Upskill. Data Education DC is a nonprofit where, similar to our meetup as well, their goal is to democratize deep learning and AI. And the hands-on coding version of that is, I think, Upskill, where they have a coding session on weekends, usually, or before the outbreak started at least, where in the weekend you'd learn something tangible and you'd walk away with coding experience. Cool. I know we have a lot of people today, but if you don't mind just saying your name and if it's your first time or if you've been here before, and what brought you here today. So I'm gonna kickstart it real quick, and we're gonna keep it short. My name is George. I'm the founder and co-organizer of this meetup, and I enjoy coding deep learning and applying it to interesting challenges like the one we're going to see today with the Cassava dataset. I'll hand it over to David.
Hey, I'm David Patton. I'm also a co-organizer of the group. I'm a data scientist and love writing models and coding and full stack work. And right now I'm working in applications to the medical and healthcare fields.
Cool. Robert?
Hi, I'm Robert Craig, also a data scientist. I've also been working with George and David to co-organize this meetup. Really excited to learn more about deep learning.
Cool. Kathleen?
Hi, I'm Kathleen Perez Lopez. I was an image scientist, got interested in CNNs and deep learning, and was leading with a couple other guys, deep learning working group. And we stopped during the COVID, and George and Robert and David took over got into this group. So I'm just really interested in learning more about it. I hope to spend more time on it.
Awesome. Welcome. Olivier?
Yes, Olivier. I'm new to data science. I'm transitioning to that career, actually. I'm very excited to start that. I have the overview of everything, but no practical, actually, experience.
There should be an interesting session then. Ishan?
Thanks, George. Yeah, I'm sort of on the same boat with Olivier. I'm probably a lot newer than he is. And yeah, I'm excited about artificial intelligence and machine learning and deep learning. Looking forward to learning everything from you guys so that I can someday do what you guys are doing.
Welcome, welcome. Vincent?
I'm Vincent Rodriguez. I am new to the group. I'm very interested in learning more about TensorFlow and getting into that. I've done some very high level or very more, I guess, regular statistical based machine learning and looking to do more deep learning type things.
Awesome. Welcome.
Thanks.
Nadir?
Hello. I'm new to the group and looking to learn more about TensorFlow. I did take one of the Andrew Ng courses and completed that, and just now just looking to start learning to apply the stuff.
Awesome. Which course did you take?
The intro course to neural networks.
Okay, cool. Hope you're enjoying it. Catherine?
Oh.
I'm Catherine Olson. I really enjoy data science and coding, and I've been attending the sessions for a while now. I'm really interested in deep learning, and so I'm here to learn.
Cool. Alana?
Hi, I'm also I'm relatively new to the machine learning and data science field myself too, and have done a few projects kind of on my own within the last year or so, but like everybody here, pretty interested to get into more practical deep learning and see some examples of that firsthand.
Awesome, great. Stephen?
Hi, everybody. Steve Milligan. I'm kind of a regular for some of these things. By day, I'm a program manager and agile coach, but my area of focus for AI machine learning is actually on the deployment and commercialization edge. I have a number of NVIDIA GPU platforms and other end devices for deploying models, and I spend a lot of time on that. And just give myself a little plug. August 1st, I'll be doing a brief talk on using containers to simplify environment setup for things like PyTorch and TensorFlow.
Awesome. Kenneth?
So, hello, I'm Kenneth. This is the first time I'm here in this group. I've been a member of AI meet and greet for some months though, and been going there. Yeah, my curiosity about this group has increased more and more, and now I was interested to see that you guys are starting to look at code and whatnot, which is something I would be interested in, looking at all this code and learning a bit, about the practical stuff. I've been doing some hobby project here at home that is sort of relevant to what the subject is today, where you have to distinguish between classes that are kind of similar. So that was extra motivation. Yeah, and normally I am a research engineer at Walter Reed, working with cochlear implants. And so sooner or later, I'm going to go from images to audio and try to play around with that.
Great job. Welcome.
Thanks.
TV?
Hi, I'm TB Kelcha. I'm kind of two things. I'm a software developer at a precision agriculture company. And at that company, we do we have some projects related to machine learning and agriculture. So this one sounded very interesting to me, but I cannot talk about those. And also I'm an artist and I'm interested in applying machine learning techniques and artificial intelligence techniques to making art. And I'm mostly interested in generative adversarial networks and natural language processing.
Great. Yeah, I remember your presentation on GANs. Really interesting.
Yeah.
Thank you. George? George Zhang? Can I get back to you? Jai?
Yeah, hi. My name is Jay Shankar. I'm actually new to this group. I'm looking forward to learn the deep learning techniques and the software programming and trying to apply it in a project. So excited to get into this.
Welcome.
Thank you.
Double R, RR, not sure that's your nickname or your headphones. Okay, we'll jump to EFM.
Yes, hello. Good evening, everyone. Yefim Shuf, joining this group's events, I believe for the third time. I remember I caught a portion of the time series event, which was great, and a slice of the event when you guys invited a distinguished speaker.
Awesome.
About myself, very passionate about analytics in general, data science, machine learning, as well as systems and security. My hope is I want to learn how what I know applies to the problem that will be discussed today and hope to learn more. There's always a lot more we do not know than we know. Thank you.
That is so true. Welcome again. Will?
Hello, I'm Will. I joined the group during the previous course and am interested in seeing just how people are applying the machine learning concepts and deep learning to actual problems, as opposed to sort of the training problems and learning problems that I've seen so far.
Cool. Welcome, Will. Kanchan? I'm sorry if I'm mispronouncing your name.
Hi, I'm Kanchan. I'm a recent graduate from George Washington University. I've just completed my master's in data science, and I'm new to this meetup, and I'm interested to learn more about machine learning, AI, deep learning.
Awesome. Welcome. Laura C.
Hello, my name is Laura. I am new to the group. I am interested in transitioning to a career in data science within the next year.
Awesome. Welcome. Bill?
Hi, my name is Bill Edison. I'm a past regular attendee at various data science meetups, new to this group. I'm a system architect and developer, mostly working in geospatial things recently, but have an interest in this area too, so wanted to check it out.
Awesome. Welcome, Bill. Jeff O'Connell?
Yes, hi everyone, Jeff O'Connell, first time member of the group. I work mostly in computational and statistical genetics and genomics, and these tools, AI, ML, DL, are being used more and more in my field, so I'm here to learn about them. Don't have any knowledge at the moment. Thanks.
Great. Welcome. Tammy?
My name is Tammy, and I'm new to the group. I work as a business/data analyst. The majority of my time is working on visualizations in Power BI and Tableau. but I'm totally interested in getting more involved with machine learning, as well as the deep learning and artificial intelligence.
Awesome, welcome. Alex? Not sure that's your name or your nickname. Peter?
Oh yeah, hi. I'm Peter. I'm a regular member here. I'm a software engineer, but I've been studying, and I'm really looking for a good application of machine learning at my job, because I think there's lots of areas that would be useful in.
Awesome. Kevin? Okay, we'll go next person. Salman?
Hey everyone, my name is Salman. Well, it's my second meetup, and I'm preparing for the Tensorflow exam as well.
Good to see you again, Salman. Martin?
Yeah, I'd like a delivery, large pepperoni and sausage, 10 wings and curlies. Thanks.
Is that a pizza classification task? That's next time. Chuba? Martin is a regular for those who don't know him, and he's funny most of the time. Chuba is not muted. Giant?
Hi, my name is Jan. It's AM from where I'm logging in. I'm working in Saudi, Riyadh, Saudi Arabia. I enjoy, and this is the first time to this group, any meetup groups. I've been working on based projects for a while. I'm quite interested in those activities. Thank you.
Awesome. Okay, that's, I think, everybody. I apologize if for some of you the mic didn't work or you didn't want to speak up. Again, I want to make sure that you're all feeling welcomed and this is fun and engaging for you as it is for all of us. Great. With that said, we have this slide here for content from Coursera Deep Learning AI. I'm not sure if you have any content today, but this is just a boilerplate that some of the visualizations and charts that we're going to see are from their platform, and we just want to pay attribution to them. And for this meetup and for the last several months, we've been using TensorFlow, which is an open source end-to-end machine learning platform. You can use it to solve computer vision problems. You can use it to solve natural language processing problems. You can use it to solve time series problems, or even structured data, as we'll see in a couple of weeks soon. In terms of setup, what do you need to code this data set that we're going to talk about today? You can do it on your computer. Given that we'll be working with images, you might need, or it's actually advised to use a graphical processing unit, a GPU. For that, you can use Colab, which is a Jupyter notebook that is hosted on Google Cloud, and you don't need any resources. It's completely free. You can run it for up to 12 hours at a time without any issues. And you get some decent amount of CPU, RAM, and GPU, and even TPU for more advanced applications. Another version of this is Kaggle kernels, and I think Robert and David may have a little bit more experience than me in that. So if you prefer your own setup, Colab or Kaggle, they're absolutely fine. If you're more
Sorry, I have a quick question though. I know you said Colab, but what if you already have Jupyter Notebook on your machine? Can this also be used as part of this workshop?
Yeah, absolutely you can. You just need to install TensorFlow, the TensorFlow library, and the TensorFlow dataset, and yeah, you should be good to go.
Is it an import TensorFlow, or you just?
It's an installation step. Actually, you need Python as well. So you need Python, TensorFlow, and I think a few other libraries to follow up. So in the code, you'll see exactly what libraries we're going to import.
Okay, I already have Python and such. Okay, cool.
Okay. Good question. Great. Then for this first week coding session, we will be looking at a data set from the cassava plant. I think this project was done a few years ago in the sub-Saharan region in Africa, where this plant is used as a backup plant, basically as a secondary primary or as a secondary source for food, in case the primary source for many families is not yielding crops. So the issue with this plant is it can be affected by different plant diseases, and once it gets affected, it actually impacts several other plants nearby. So it's very important for farmers to detect it quickly and accurately, and use different ways, probably isolate or maybe eradicate this infection so that it doesn't impact the entire farm and they lose this really important crop for them. And if you remember our conversation with Lawrence also said that this was one of the interesting applications that the TensorFlow team, as well as university from both, I think Madagascar, as well as from university somewhere in PA, had collaborated together, and they labeled different leaves, and they labeled them by different disease types, as you're going to see. And the thing with this disease is that it progresses over time, so the sooner you catch it, the better it is for the farmer. And the cool thing is when they deployed this model to detect diseases, they deployed it on a phone, a low-power phone, so that you didn't need a GPU or a high-expensive computer like we're going to use today to actually do this classification. You can even do it on your end device. For next week and for the next couple of weeks, I'm briefly going to mention a little bit about some other sessions. So next week, we're going to talk a little bit about annotation and NLP. If that's something that is interesting to you, please join us next week. I will cover this in detail in the very end. Then we're going to take a deeper dive into NLP. We're going to look at different scripts from the famous TV show Friends, as well as Big Bang Theory. We'll try to classify emotion based on pure text. Then from the structured data set perspective, usually you see other ML or classical statistical approaches perform really well. We will try that as well as a deep learning approach to detect fraud in about 250,000 transactions from credit cards. And then finally, we're going to top this 5-week challenge with a time series prediction. We're going to look at weather data in Madrid using classical ML as well as deep learning. And we have a surprise in the end. We're still working the details side of it, but we're also working on a private data set that is COVID related, and hopefully we should have access to that private data set and be able to explore it with you at the end of this 5-week challenge.
George, I was looking at the data sets from that CAIHA, I think it was, a list of data sets, and found some really interesting stuff about emotion detection from the facial stuff. So for the slide before that you just showed, the Big Bang Theory, the emotion annotation, do you know what you plan to use to recognize the emotions, or is that the one where you were talking about that we would code it ourselves?
Yeah, so my plan there is we can either listen to audio or look at a video clip, and we'll also have the corpus of the text corpus in front of us. And the goal is for us to label and annotate the emotion of each sentence, and there's like 5 or 6 categories we're going to use. So we'll be basing it based on audio as well as video.
I'm just wondering if some of the facial detection and emotion detection that I'm finding might be interesting for that, to apply to that.
Yeah, I'm happy to explore that as well. If you're able to, if we're able to find a data set that is already well packaged, I would say, I would absolutely be interested in exploring that.
Okay. I have a PowerPoint with a bunch of data in it. It's probably better if I clean it up a little bit and then put it on Slack.
Yeah, and maybe next week when we talk about that, we can talk about this project as well.
Okay.
Yeah. Awesome. Cool. Let me give over the floor to David and Robert. I'd love for them to give us an idea of this data set, of what is it comprised of, and just for understanding, there are slightly two different data sets that you can work with. David, why don't you kick it off?
Yeah, I'll take it. So the first one, you can pull it from TensorFlow's own, what's called TensorFlow data sets, and they have an image classification listing of directory, and one of the ones in there is this Cassava data set. In there, they, if you remember from Lawrence's course, there's what are called splits, and when you pull down a data set, when you load a data set, you can choose what split you want, or you can get all of them. In this case, the data is split between a train, a validation, and a test set. In total, there's 9,430 labeled images. The training set is about a little over 5,000, and then the test set is around 2,000, as well as the validation set is 2,000. In this case, all of the sets are labeled. So you've got images and labels in all those sets. The other alternative is to use Kaggle's data set, which was used in a contest there, in a competition, what they call a competition. And you can still upload your predictions for their test data set to that competition and see how well you do. The competition is over, it's closed, but they'll still score your submission. In that data set, there is a training set of labeled images that's the same size as the one on TensorFlow. And in each of those, it's got directories with all the labels for those training images. There's a test set of unlabeled test images, which you would run on and predict the labels and then submit that. That test set happens to be 3774. We'll come back to that number in just a minute. But in addition, the one big difference between this set and the one on TensorFlow is in the Kaggle one, they provided a set of extra images, and these are unlabeled. They're 12,595 unlabeled images, which you could use as additional training data if you can figure out how to do it. And we have some ideas around that. So coming back to the set of test images, I don't know if anybody's figured it out yet, but you could backwards engineer this and figure out the labels for all those test images in Kaggle and score a perfect score. Because if you notice, if you look at the TensorFlow data set, the test set and validation set, if you add the numbers up, they equal exactly 3774. So I imagine you could do a matching process and figure out what the labels are in the Kaggle one. But that would kind of defeat the purpose.
Interesting. I didn't realize that, David.
Yeah.
That may not have been quite so obvious at the time of the competition.
I don't think they, yeah, I think the TensorFlow data set was not released until after the competition on Kaggle was run. So
you're saying from the image, from the file name, you can detect the class?
I don't know if it's
or the number
clear from file name, but I think you could do some analysis of pixels and figure it out pretty quickly. Yeah, I didn't try it, but I'm sure I did add the numbers up, and it looks pretty good to just be coincidence. The only other difference, really, and maybe people, if you're working on this, you might have to deal with, is the files on Kaggle. After they close the competition, they zip the files up, I guess, to save space. So you'll have to unzip them, and if you're doing this in some kind of environment like Colab or even on Kaggle's kernels, you'll have to figure out how to do the unzipping. But so if you need help with that, just reach out to us. Last thing I wanted to show was I looked at the Kaggle training set, and they talked in the description about the classes being unbalanced. One particular disease, I think actually two diseases made up, was it 70-something% of the classes of the actual images. And here I just plotted out, I looked at all the classes, and number 4 there is the healthy classes, and 0 through 3 are different ones of the diseases. They're in the alphabetical order that George is showing on the left. So I just want to show the unbalanced nature of this data set. Something you might want to take in consideration when you're coding.
David, may I ask you a quick question? Is that okay to ask you now, or should we wait till the end?
Anytime is a good time.
Do you know what was the methodology for taking the pictures from the plant, like such as number of pictures per plant? And for so that's one. And the other one is for the plants that were diseased, that had a disease, whether the pictures were taken from the neighboring plants or plants that are kind of spread out across the field. And the other one, in real life, if you take 10 different fields, what would be the actual distribution of these diseases? So these three questions I can repeat if you want.
No, that's okay. I think I understand the three questions, and I don't actually know the answer to any of them. I did not see that listed anywhere.
Good enough. Thank you.
Would it be helpful to take a minute or two to look at some of these images? I was kind of taken aback by how difficult this would be to do manually. Yeah. I think this is one of the reasons why the task was presented as such, because most farmers who have these kinds of plants, it's extremely difficult really to tell what's going on. If you'd like, I could share my screen. I actually have all the images downloaded to my hard drive. We could step through them.
I can just start by showing two out of each category, and then you can take over.
Okay. Yeah. If you've got each category represented there, that's good.
Yeah. So I'm just pulling here two images out of each category. This is healthy. This is healthy. Then the first disease, CVV. Even for humans, kind of hard. I guess the structure of the leaf is a little bit different, and it looks a little bit rusty here.
I think BB was bacterial blight.
Okay.
What it seemed to me that those ones tended to have in common were these little spots on the leaves, dark spots, and often very difficult to see.
Yeah. Then for the second one,
the CBSD is the brown streak disease, and it looked like in many of the leaves you had a little. Maybe the tip had kind of browned and it didn't look green anymore. But then many of the examples that were labeled that way, I didn't see that at all.
This one looks a little bit bumpy, but I realized it's not bumpy in the second one. So maybe bumpiness has nothing to do with disease. You see these little puffs.
Right.
It could also be where it is in the progression of the disease. I don't know.
Then another one which looks more drastic.
This was the green CGM, was a green mite disease. The thing that these images seem to have more in common to my eye was these little light colored spots on the leaves that are more evident in image 97 there.
So little dots, but a lot of them.
Yeah.
Uniform.
And then CMD, the next class, was the most common one. And that was, I don't even remember the name of it off.
So yeah, there's clear deformation of the leaf here.
I got the feeling these were taken by cell phones so as to be compatible with what the end goal of putting an application on the cell phone was. I don't know if you guys think that's the case.
And that was certainly the end goal, was to deploy the software to a cell phone. I think many, with the different sizes and shapes, I think, yeah, they could have been a number of cell phones.
Do you want to look at more examples, Robert?
No, I just thought it would be helpful for people to to get some concept of the level of difficulty of this task.
That was a good idea, Robert. That probably should always do that in everything.
So the idea here is that we have to be able to distinguish between all 5 of these different types of things.
Yeah, do it pretty quickly. The gentleman who asked the question about, what did you know about how they collected the data? I thought that it was a good question, and just kind of going forward, if we can shed it, like this one, this is a kind of a rare data. This is a data set, for example. I might have been able to create if I was in the cassava field, you know, over the course of a month or something. Like a lot of these, forget it, you know. But if we can, you know, give some thought to what qualifies as a good data set, you know, we hear David was talking about the imbalance of the data set, and I'm curious about, and sometimes you get very extremely imbalanced ones, like in credit card fraud and in like the electricity fraud that we were talking about. You know, the frauds compared to the ones that aren't fraud, it's a very small proportion, and just give some thought to like what is the theoretical effect, you know, and you know, if you're creating your data set, is there a good way to do it? So food for thought.
Sure.
There's a great message in the chat, by the way, from showing a little bit about how they collected the data, if anybody's interested.
Yeah, there's a video as well. Yeah, we have a link on the meetup of how this happened. It was very, very annotation intensive from what I saw, right? You had to label physically, you had to draw squares around each region where the plant was impacted.
So George, David, and the folks that looked at it, the data and description more thoroughly. So from the practical perspective, if a plant has a disease, that plant has to be removed regardless of the disease, or some of them can be treated, so to speak? From a practical perspective, does it matter which disease is or not? Basically, what's more important to the farmer, healthy, not healthy, or they really need to know whether it's healthy, and if it's not healthy, then there is a different, you know, pathway for mitigation, so to speak.
So I think, if I understood correctly, if I remember correctly, these are sorted by severity. So some of them I think can be treated by maybe medicine, but some of them are so intense that you actually have to remove them so that they don't impact their neighborhood. So that's why it's important for the farmers to realize at what stage their plant is, so that if it's on the early stage, they can probably treat it. But if it's later on, they might as well just remove it.
Okay, so from a training perspective, for some of these cases, false negative have more severe impact, so to speak. That's what you're saying, right?
Yeah.
Okay.
But George, a question here.
Let me pull the video.
Has anybody opened up the data set or examined it using something like Visual Studio or another tool? Because I guess, you know, when I look at the descriptions, it says that, you know, there are X number of labeled test cases. But for instance, has anybody looked in to see, you know, basically to characterize what those labels are in the data set? Because that would seem to give insight in terms of, you know, what you can do inference on.
So,
and tell me if I'm not making sense. So, you know, the first thing I do, I mean, I'm a programmer. The first thing I tried to do was to see what type of data set it was. So for instance, if it's JSON, if you just feed the URL into a browser, you should see, you know, it should spit the JSON back from the API.
Got it. You're talking about the data structure, right?
Well, I'm talking about, yes, it's examining, you know, the structure of the data as it sits in the file. You know, is it a CSV? Is it JSON? What is it? And then the next level down, examining the labels to see, you know, basically what, you know, is everything that it says is labeled. You know, how descriptive are the labels for the training set?
So the files come in a zip file. When you unzip them, they create a directory structure, which we were kind of showing there a little bit. We didn't really say it, but the names, so the training has a subdirectory for each type of class, and in there are JPEG images. So every JPEG image that's in that subdirectory is of that class. And it's a very common way to lay out a file structure so that you can read it in with something like a image data generator.
Mm-hmm.
Does that answer your
Yeah,
question?
well, no. So David, what I'm saying is, if you just had a bunch of JPEG files, they don't naturally have, other than the title. What I'm interested in seeing is what is the structure of the data. It says in the Kaggle description that there are X number of labeled pieces of data, right?
Yeah.
Yes.
So you're going to have some structure, and I noticed in some places they mention CSV or comma separated, but nowadays most of these files come as JSON files, which means you're going to have tag value pairs, and then I would just walk through those to see what they were, because that's basically what I can write a model against.
Got it.
So here the tags are the directory names, if you think of that, and the values are the actual images. They have in fact included the labels in the image file names as well. You don't often get that, but you could. So you could also sort that way. So every image is labeled by the name of its file as well as the directory that it's in.
I would assume that before the competition, they did their best to try to scrub any metadata from the JPEG files that might be useful.
For the test files, yeah.
Mm-hmm.
That's why I asked about the location of the plants.
Right. Is there something in the EXIF data that's, yeah.
Yeah, because once you know, if you tell me that the disease spreads very quickly, then once you know that this plant is diseased, then the neighbors have the same disease.
Mm-hmm.
Okay, maybe we're walking across terms here, because in the description, for this on TensorFlow, it says that there are, let's say, 9,000 unlabeled images, but there are also 5,000 or whatever labeled images. So I would expect them to be structured so that you can differentiate the image from, you would have one label per image. Does that make any sense?
I think it's the folder name which is actually giving you the property, and that's the only one we have. That's my.
No, that's what I was asking. If you'd opened it up in some, you're not going to see it that way. You'd have to open the actual data set in an IDE, in Eclipse, or in Visual Studio Code is what most people use to see it. And then you can actually examine the structure of the file itself.
Do we have anything else than the zip file? That's what the data set is about, just a zip file?
Yeah, Steve, I think we're jumping ahead. Do you mind if we
the property?
Yeah, I think we're jumping ahead. Can we take a break, please? Yeah, I think we're going really into the data part. I understand. There were some questions around the diseases and all that. That's why I was trying to answer first. But if you're ready to jump into the data part, it's next on our list. I'm not sure if I answered all the annotation or other questions we had, but I think we're ready at this point to just look at the structure from the Kaggle perspective or from the TensorFlow perspective. I don't want that distinction to confuse us. For us, the challenge is we have labeled data, and that labeled data belongs to 5 categories, and you need to build a classification model, the computer vision classification model, to distinguish between these 5 categories. Now, how many training set we have, what is the size for each data set, Kaggle or TensorFlow, that's to me of second importance. To me, most important is what is the training set, how does it look like you said, Steve, and how can we use it? Okay, so should we just dive into the Colab, Robert and David, or is there anything else you want to cover before we go there? We have some slides here on transfer learning and all that. Should we talk about that later?
Yeah, we can show those later, I guess.
Okay, I can start with my notebook. I posted it on our Zoom as well. Let me close on this. So Steve, in terms of structured data, Once you download it from Kaggle, you're getting zip files. You're getting a zip file for the training set. You're getting a zip file for the test set, which is unlabeled. You're getting another zip file for the extra images data set, which is also unlabeled. So from a deep learning perspective, from a supervised learning perspective, the train zip is the folder that we need. And once you download that and once you unzip that, I'm downloading it here in Colab. Once you look inside train data set, you will see 5 different folders. You'll see one folder for each different class or disease. So one for the CBB, one for CBSD, CGM, CMT, and one for the healthy. And within each folder, you're going to see a collection of JPEG files. And the name is usually train, the class, and an index. So train healthy 1, train healthy 2, and so forth. So you just basically have at your position, you have this position, you have collection of JPEG images structured by folders. And that folder is the tag that you're looking for. That's the class name that you're trying to predict. Does that make sense?
Yes.
Awesome. Unfortunately, for the test set, if you look at it, it's just a collection of JPEG files. Like, I'm expanding it now. There's no label for the test set, so we don't know what we're looking at. We can use our model to do prediction, but again, how accurate based on the accuracy of our model, we can get an idea. So test is just test, image, and an index, and it could belong to any of those 5 classes.
I think the test was the one that they were scoring the algorithms on. Like you make your algorithm, then for each of the test images, you say category 1, category 2, and so on, and you submit the result.
Yeah, so for the Kaggle, they have a sample submission file. Yeah, you're right, where you specify the name of the test image and the category. So that's how you submit it in Kaggle. But we're not going to do that in this coding example. Cool. Does that answer all the questions about the structure of the data? It's just 2 folders, and the training folder is actually structured in a way that each subfolder is the name of the class of the disease. Awesome. And let me minimize this. And let's go over, at least in Colab, how would you start doing this? Let me zoom in a little bit so we can see better.
Might have to do it with your Control+.
Yeah. Is it legible?
Looks good.
Awesome. So the Kaggle dataset is there, and in my notebook, I'm only working with the Kaggle dataset. I think Robert David also worked with the TensorFlow dataset as well, so I'm curious to hear their thoughts. So for me, working with Kaggle on Colab, there are a few things I need to take care of. One of them is I need to import Google Drive. Google Drive is basically my storage in Colab. Since Colab is typically a virtual machine in Google Cloud, it's ephemeral. You need some kind of persistent storage. So with Google Colab, from Google Colab importing Drive, you're actually mounting a Google Drive in your Colab. The other thing you need to do is if you go to your Kaggle page, and if you go to your, let me zoom out a little bit. And if you go to your settings, I don't think there's anything proprietary here, so you can see. You have to select this create new API token. That will download a kaggle.json file that you need to place somewhere in your Google Drive, and I placed it for me under Colab Notebook/Kaggle. And that JSON file is basically an API key that authorizes Colab or any other SDK, any other programming language to contact Kaggle or your account in Kaggle and do something. Do something, you can list your data set, you can list your notebooks, you can download data set, you can do all kind of programmatic actions from code to Kaggle. So basically like Kaggle as a service. We're only going to do one thing with this API access. We're just going to download a simple data set from Kaggle. So I'm storing this local path in this variable for me, Kaggle Google Drive path. I'm storing it as an environmental variable in Python under the name Kaggle config dir. And I'm looking at the different structure. This is after I downloaded the data. If you just look at it before, it will be empty. There's nothing there. And this is the command that you use to download this specific data set from Kaggle locally to your Colab environment. So it will download the training zip, it will download the test zip, it will download the extra images zip, the sample submission file, some random text that I think is some description. So basically the zip files that you need from Kaggle. You might as well go to Kaggle and download them manually and import them in your Google Drive. You can do that as well, but this is like more like an automated way to do it. Then with these magic commands in Colab, magic, anything that begins with percentage, it's like a bash command, like a command line in Colab. If you look at it, you would only look at the zip files. So the next step to do is then unzip this training.zip and test.zip. Not only that, but I also want to track separately the different folders where the different categories under train are. So I need a folder for the healthy one, for the CBB, for the second, the third, and the fourth different disease. And if I look at what is their size, for the healthy ones, I have 316. For the CBB is 466. For the CBSD is 1400, 700, 2600. And what are some sample names from those different categories? And if I want to look at 2 images at a time, we know the folder name, we know the file path. We can just look at two files at a time. We can print their exact path. So under train healthy, we have a healthy image, another one, the CBB, another one, the third category, and the fourth category, and the fifth one. So this is us exploring the data and trying to understand the structure of the data and trying to understand how these images look like, if they're like high resolution, low resolution, exposure, brightness, contrast, background, and so forth. So it's a little bit of variety. Like this one looks a little bit of lower quality compared to others. Great. Then if you remember, any questions so far before we jump to the actual analysis and how we use this data? Okay. If you remember from our TensorFlow in practice, this structure of data is excellent for this class or object image data generator in TensorFlow. What that means is that this image data generator would read the structure of our data and you'd tag it for us. We don't have to label the data. The data is implicitly labeled by their position in these folders. And what this image data generator will do is we'll pick files from these folders and it will remember which folder it picked it from and it will assign their label accordingly. So for me, the first thing that I did is I specified where the training directory was. For me, it's under temp train in Colab. And I created an image data generator. And you can do different, what is called data augmentation or image augmentation. And we've seen in the past that that helps a lot with avoiding overfitting. So what that means is that you're rescaling the image on the fly from, as you're doing training. You're taking the raw image and you are rescaling it. You're making it smaller or larger. In this case, we're just dividing by 255. You can rotate by a range from 0 to 40 degrees left or right. You can shift it, the width, you can shift the height, you can shear it, meaning you can make it from a square, or a rectangle, you can make it like a rhombus. You can zoom in or zoom out, you can flip it horizontally. And for many of these actions, if you do that, you're gonna be left out with a patch of the image that there's no pixel, there's no content. And image data generator has an attribute called fill mode, where it tells you, how would you like me to fill this empty content? Would you like me to do a specific value? Would you like me to look at the nearest by pixel and just fill them in, or different fill modes? When I started coding this, I borrowed some code from our TensorFlow in Practice specialization, and that one had a validation directory. In this case, we don't have a validation directory, but this was just me trying to take a quick look of what's going on. So if we look at the training directory, there's 5 images in 5 classes. Yep, go ahead.
So one thing that's never been cleared about this data augmentation. Let's say that if you have a rotation range or some horizontal flip, that's kind of easier to understand.
Mm-hmm.
So, and say that your training data set is 10 images and you have horizontal flip set to true. Does it mean that you're going to end up with a training set of 20 images?
No.
Or are they going to be randomly flipped?
So each time you're going,
still going to have 10 images, but some are flipped and some are not flipped.
That's right. Some will be flipped. It's a random pseudo-random generator that does it, but you'll have the same size number of images in your batch, and every time you do an epoch, it's going to choose a different image and perform a different augmentation to it. The idea is that your model will now get to see more data, right? So we're hoping to avoid things like overfitting by doing this.
Okay. Oh, so on each epoch, some of these transformations may be applied randomly to images.
Yes.
My understanding is that essentially every transformation is applied, but some of them end up returning essentially unchanged data. Like the zoom range is 0.2 means you could zoom in 20%, or you could zoom out as much as 20%.
Sorry.
You're doing that based on a random number that is chosen between -0.2 and 0.2. So, I mean, the chances that you're going to end up with exactly the same size are pretty small. In the case of the flip, where it's a discrete number of choices, then it's a coin flip, basically.
So, kind of a follow-up question, if it's okay. Is it better to do this kind of data augmentation on the fly, or kind of prepare the data set before by performing every single augmentation? Because that's what I was doing before, like I would take the images and do every single augmentation, and I would end up with, if I would apply 3 augmentations, I would end up with 8 times the size of the data set. So which one is better? I'm wondering.
So part of the reason we do things with image data generator is to do things in memory. And you're also doing it one small batch at a time. So traditionally, this is more appropriate for very large data sets. If it's not a large data set, you probably can train faster by doing this one time. The thing is here, as Robert said, these are random, generating random augmentations. So you're getting a lot different looks. I don't know how many things you did as far as how many augmentations you did and how random they were.
And you're also getting a new random combination each epoch.
Right.
Okay. Yeah, I understand. I was usually doing very few flipping and a little bit of brightness.
Mm-hmm.
Yeah.
But I have a question. So you randomly apply some transformation to each of the images, and where the null transformation is that you don't do it. But there's each epoch you have the same, each of the training images provides just one entry into that data set.
That's right. Yeah, you will not, each epoch and actually each batch will be the same size whether you do the augmentation or not. It's not, you're not increasing the number of, you're just changing out the images as a way to think of it.
But if I have images like A, B, C, D,
Mm-hmm.
I still get something from A, something from B, something from C, and something from D.
That's right.
may or may not be transformed. I wouldn't get two different transformations from A and B and C if I had a batch size of 4. Is that right?
Yeah, it's a 1-for-1.
Okay.
Awesome.
Just a quick follow-up on what TV was asking. So what's the reason for doing a random transformation, but just not to apply it exhaustively to ensure that the model captures, the variety of possibilities? Is it purely like lack of resources or what?
So if you look at the images, this is to avoid, I think, some kind of bias of how you took the pictures during training and how you might see them during test.
No, I know, but what I would do is exactly, and what I was doing typically, like TV was saying, is to do it for every single image through a variety of combinations, not by randomly applying, because we don't know what the test set will look like and at which angle the picture was taken. You see the point?
Yeah, so your goal is to try to make your training set as similar in distribution as a test set. Like, that's why you're doing this transformation, because your training set could be very well positioned pictures where the camera is right on top of the plant, but in reality in test, when a farmer goes to take a picture, he's not going to go exactly on top of it. He's going to go a little bit to the left or to the right, maybe flip his phone. Like, there's so many variations that he can take a picture of.
Right. So
the other
I'm
thought is,
asking
so you're
a slightly
talking.
different question. Why not do this transformation, say, at every 10 degrees of an angle for every image?
You can, yeah.
So, okay, so it's a purely trade-off
it's
of model accuracy or quality of a model versus trade-off with respect to storage.
Oh, there's another reason, right? So we're trying to not have our model overfit the training data and then do poorly on the test data. So if I just systematically go and produce a bunch of data or images where I just rotate them all, and then I train on that, I'm not actually, it can overfit that as well, right? So the reason we're doing this in a random nature is so that it picks out key features from the images, but it doesn't overfit them. Does that help? Does that make sense?
I understand, but it doesn't quite answer my question, but that's fine. Go ahead.
Yeah, so you're saying, why don't you, let's say you have 1K training images, you want to do all or as many possible combinations of, shift, transformation, rotation.
Yeah, let's just take a simple example. You have only 10 images to work with, not 1,000. You have 10 images to work with, right, as a training set. So what you would want to do is you would want to rotate them all possible way and crop them and chop them so that you create as many training slices as possible. And that would be a good starting point.
Yeah, you can do that.
So that's why I was asking whether it's a trade-off between like resource constraints and time.
You can do that. As long as you shuffle when you train, you should be good, I think.
Thank you.
But I will say just that even if you did that, you're still risking overfitting because your training data is now no longer changing. It's the same training data every epoch. So that's why we use a random augmentation. So it's not just resources is one reason, but the other reason is we want to introduce that, hey, you're going to see new images every epoch that images you've never seen, and that helps from overfitting. I don't know, maybe we can talk about it later, but maybe not.
No, I mean, I think
analogous
that's a very
to
good
the
point.
argument of why one might construct a random forest as opposed to a really carefully designed decision tree.
Right.
Great. So we're doing these transformations, and so that's on the data preparation side. Then we go to the actual modeling side, and we need to figure out, so this is a computer vision challenge. So we need to figure out what model can we use. So we're going to use a convolutional neural network, which is really good at picking up features from images and detecting, let's say, horizontal lines, vertical lines, edges, shapes, colors, textures, different things that could excite the network, basically. And this is a very basic custom network that we worked in the past several times. It is made up of 2 building blocks. One is a 2D convolutional neural layer, where you have what is called a kernel or a weight, 3x3 weight matrix, and you apply that to your input image, and you have 64 of them. You apply that to different patches of the image, and you're trying to detect features as you scan your image. You can pass them through an activation function as well. In this case, we're doing the ReLU, which is the input if the input is positive, or 0 if the input is negative. And we will also reshape our input images to a specific size. This is important because your network expects a specific size. This number, you can change it later on, but let's say our images are 1K by 1K. You'd like to minimize, or you'd like to keep the number of the size of the input size as small as possible so that the network can train a reasonable amount of time. I think if you give the raw data, as long as it's the same, I think this would take a long time to train. Is that true, David, Robert? Let's say all images were 1K by 1K.
Yes, if you went with large like that, it'll take a long time. But you do have to standard, they all have to be the same size for training.
Yeah.
For this.
So that means that you might have to do some kind of padding, or you might have to do some kind of clipping just to make sure that the size of the image is the same. And this network does that for you. That's the interesting part of it. This the image data generator, when we specified above, as well as this input shape here does that for you. Then you do something called max pooling. So you'll end up with a smaller image from, let's say, the 150 by 150 input. You'll end up with a smaller image. You want to cut the size of that image in half by picking up the max pixel, or the pixel with the highest value from a region, and that's the purpose of this layer. You do this multiple times, and we'll see the shapes of the data as it flows to the network. But you do this 1, 2, 3, 4 different layers, and then in the end of the day, you're going to end up with. Let's actually look at the summary right here. So the input size is 150 by 150 by 3 for RGB channel. When you do the first convolutional layer, you can't really use the outer part of the image because this is a 3 by 3, so it's not defined. So you actually have to look at the 148 by 148 part of the image. And you have 64 such filters. You're doing basically this convolution 64 times in parallel. So the output shape after the first convolutional layer will be 148 by 148 by 64. And that has about 1700 parameters. This output shape will be cut in half once you do this max pool in 2D. Then the outer perimeter will be removed again. So you'll drop 2 pixels from the width and the height. Then we'll be cutting in half again. Drop 2, cut in half. Drop 2, cut in half. So now you have a 7 by 7 by 128. So let's do some math here. 7 by 7. So 49 times 128. Sorry, did I do it wrong?
I think you had an extra term in there.
128. Yeah, sorry, I put 7 too many times. So you'll end up with about 6K different parameters, or that's the input size. But it's in a 3D shape. It's 7 width, 7 height, and 128 is the channel. You want to flatten that. Basically, you want to represent this whole 3D object or 3D matrix as one long vector. And how many items do I have in that vector? Width times height times depth. That's 6K such values. So that's the flatten. That's the purpose of the flatten, to convert this 3D tensor or 3D input to a flat input. Dropout will randomly drop some of the neurons between the previous layer and the next layer, and you can specify what is that percentage of, let's say you want to drop randomly 20% of your connection between different layers. And then
George, the steps you're describing here, this is your hypothesis of what would be a good model? I mean, these were your choices, right?
yeah, this is just a very basic model from scratch. We're going to look at a more complicated ones, but this is like a baseline. What's the simplest model with, let's say, a few million parameters, 3 million parameters? What is the benchmark I can get out of it, and how do I improve on it?
Okay.
Yeah.
George, will you be looking later on at a transfer learning application?
Yes.
Okay.
Yeah. So this is from scratch. Yeah. We're going to look at transfer learning as well. Then a dense layer, and the last dense layer will have to be 5 output, simply because our categories are 5. And if you look at here how many connections we have or how many parameters we have about 3.4 million, and all of them are trainable, meaning when we do the forward and backward propagation, all these 3 million parameters will need to be updated. The next thing we need to define in TensorFlow is the compilation parameters. We need to define a loss function so that when we look at our prediction and what is the true label, how do we assign a value to that? We need to look at the optimizer, which tells us once we have the loss function, how do we actually update all these 3 million parameters in a way that the next input is closer to the true label. As well as some logging. This is purely for logging metrics. What would you like to see? We'd like to look at metric, accuracy metric as we train the data. So in Colab, when I do this under runtime type, you can specify none, which is CPU by default. You can specify GPU, or you can specify TPU. So I have GPU for now. And what I'm doing here is I'm feeding the trained data generator, which has the trained data as well as their labels. You can specify how many times you want to look at the entire data set. I want to look at it 25 times. This steps per epoch, if you don't specify it by default, it will calculate it for you. But this should be your training size divided by your batch size. And for me, this is one typo that I did. I used this from another setup, and for me, this steps per epoch basically caused me to use only 20 images per epoch. Or if you do the math, I think it's about 48 or 50 images. So this is one typo that I did that didn't give me good results, but later on when I looked at it, I realized what was the issue. And then as you see here, as you go epoch by epoch, the number that we're interested in is the loss and the accuracy. The validation loss and accuracy don't matter to us because we don't have labels for that data set. And as you can see, after 25 epochs, I was able to get about 59% accuracy, which is just a little bit above random, I would say. You can save the model if you want, and you can visualize it as well. So this is the training accuracy for this many epochs. And you can also upload your own images. In this case, I uploaded 5 healthy images, and I'd like to see the output of the network of what should be. So if I remember from our conversation on Slack, Robert and David, the classes should be labeled alphabetically. So healthy, if my model was right, they should assign a high value to the very last position of this vector, right? So in my case, my model is misclassifying the first 2. Yep, the third one. So basically, it's not predicting correctly any of this for this random.
One thing that may be affecting this here is that, recall from the data set balance, healthy was the least frequent item in the training set. And it looks like your model there is predicting the Cassava mosaic disease, number 3, times, and the brown streak disease, element 1, the other 2 times. And those were the 2 most common diseases.
Got it. Yeah.
But there was another thing that struck me in the notebook. When you're declaring the validation generator, if you scroll up, there it said found 3,774 images belonging to 1 class. It seems like the validation data set is totally off kilter. So it seems like you're not validating against anything.
Yeah, that's why there's no validation data set for the Kaggle data set. If you look under test, there's only one label or one folder, and that's
Right.
what the generator is saying. There's only one class 0.
Right. So you're trying to match 5 classes and kind of somehow fit them in one. It kind of seems like it's apples and oranges what you're trying to fit with
Yeah.
this model.
Well, I realized that. That's why I didn't use validation generator on the second version of this. I have like 5 or 6 different versions of this model.
Oh, okay.
Yeah. So yeah, to give you an idea, that was version 1. Yeah, version 1 had 3 million parameters. It scored 58% training accuracy, and these are the steps that we followed. I can go through the notebook, or I can give you the high-level idea, keeping in mind also time, and also I want to give the chance to Robert and David to talk from their experience as well. So you saw that was model 1. I can maybe quickly give you the high-level idea. Model 2 is what I did is I increased the size of the network, and maybe I can quickly scroll down here. So what I did is this is version 1. Version 2 is exactly the same as version 1, but all the different now inputs, how many nodes we have on each layer is doubled. So doubled means we actually have now 4 times more parameters. From 3 million parameters, we have 13 million parameters. Same optimizer, RMS prop, categorical cross entropy, 25 epochs. Still, this is an issue. I didn't detect it back then. Accuracy, about 56%. And if I want to compare it with version 1 and version 2, it's actually did a little bit worse than version 1. So I have a 4 times more parameters, a richer network, but my training accuracy is a little bit worse than what I had before. So I'm clearly not, something is off here, and I'm not doing well. And we'll see what is off. So that was version 2. Version 3 is, I think, the one that gave me the best performance. And let's look at version 3.
Quick question. I didn't quite notice it was flying very fast.
Oh, sorry.
The images was scaled down to 150 by 150 pixels, but each convolution was slightly smaller than the actual image, right?
Yeah, it was 2 pixels smaller on width and height. So if you look at the shape, 150 by 150 will end up being 148 by 148. Is that what you mean?
Yeah.
Yeah, it's because when you play the convolution, this is a 3 by 3 kernel. You need 3 values to calculate something. 3 values horizontally, 3 values vertically. You need 9 numbers, right? You need a 3 by 3 patch. So if you put that all the way to the edge, it's not really defined for the edge cases.
Yeah, I understand. And the 58% of accuracy that you mentioned earlier, was it 58% on the training data?
Yes, everything goes in the training data. We don't have any other labeled data set.
Got it. And did you happen to look whether it was like uniformly 58% across 4 different diseases and healthy or no? Or some of them did really well and some were poorly?
That's a good point. Yeah, look at how far you're off. Basically, how off are you for different categories?
Exactly. Because we didn't look at all the images in the beginning, so I don't even know whether those were actually like 4 different types of diseases collapsed into one.
Mm-hmm.
Like 4 different flavors of this BCG disease.
Yeah. Then for version 3, I introduced another optimizer, Atom, instead of RMS prop. I also increased the epochs and to 100 instead of 25. That gave me, I'll just give you the chart. That gave me a much better performance. So after 100 epochs, I was about 72% on training set, and the other 2 versions, I just stopped at 25 epochs. So clearly there's more room here to grow. The issue here I have is that I don't know if I'm overfitting on the training data set simply because I don't have a validation data set to see how I'm doing on that. So just this line on its own is not enough for me to know that, yes, I'm on the right path. I mean, it looks like I'm on the right path, but I don't know if I'm basically overfitting on the training set. That's super important in deep learning. And the loss function, yeah, it's uniformly dropping down, but I don't know if the validation at some point increases, or is it also going down, the validation loss? That's one challenge with this data set. Then, in terms of transfer learning, I use two different more expensive and more complex networks. One is built by Google that is optimized to run on mobile phones. It's called MobileNet version 4. It has 34 million parameters. So we jumped to 34 million, 10 times more than what we had before. Very similar structure here. But now I'm importing MobileNet version 2 from Keras applications. And if you look at their website, the specification for this model is that it prefers the input images to be of a different size than what we had before. It prefers to be 224 by 224 by 3. They have another factor called alpha factor that is basically how deep or shallow your network should be. An option if you want to include the very last layer of this network, which is the output layer. And this model was trained on the ImageNet dataset, which has 1,000 categories. I'm not interested in 1,000 categories. I'm only interested in 5. So by including top as false, I'm basically dropping that very last layer of the output, simply because I want to put my own custom network on top of that. Another thing is, I do not want to train this whole 34 million parameter network from scratch. I want to freeze all the different layers and all the different weights and biases. You do that by iterating here over the different layers of this model and setting layer.trainable equals false. So then if I look at summary, the summary will be a very long one, but the input is 224 by 224 by 3. It has convolutional, zero padding, batch normalization, activation function, many other operations on it. And I'll just go to the end. It's a very large network, as you can see. We have the network itself is 2 million parameters. Sorry, so you'll see where the 34 million comes from. So the network itself has 2 million parameters. Then on top of that, I would like to add my own network. And how do I do that? I take my input. I have to specify an input layer, 224 by 224 by 3. I was reading on their website that when you use this model, you have to actually, it's strongly suggested to use this pre-processing input. And I was looking at it. I think it did some kind of scaling or pre-processing. I'm not sure exactly how that helped this model, but I used it anyway. Then on top of that, I created my own network. And basically what I did is I flattened the output of the MobileNet model. I created a dense layer with 512 neurons after that, a dropout of 50% layer, and a dense of 50 neurons as the final one. So I do that, and you'll see now the parameters, how they explode. So the model, MobileNet version 2, had 2 million parameters. But when I jump from this output, which is 7 by 7 by 1,280, that's the output of MobileNet version 2. When I flatten that 3D object, that object has 62K values in it. I want to map each of these 62K values to a hidden layer with 512 values. So if you multiply this number by this number, you'll end up with 32 million parameters, which is significantly higher than what we started with. So if you look at the total parameters, we have 34 million. Most of them, 32 million, are trainable, which is not great. The non-trainable one are the mobile version 2, and there are 2 million of them. Any questions about this? Then I use the atom optimizer, 25 epochs. I'm not able to go more than 40-something%, so something is clearly off for me here. And if I look at the loss, I was stuck at 46%.
George, for this case, you rescaled your images, right? Because I noticed the inputs were larger for this network.
Yeah, it's 224 by 224 by 3. The original images are much larger than that. They're like 500 or 600 by 600, I think.
Did you look at the images after rescaling just to see what they look like? Whether the rescaling routine does a good job, and just to be sure that Like visually, they're kind of representative?
Not for this, but I think they do. No, I didn't do it for this application. I'm curious if anybody else has tried that.
But they are usually very distorted, aren't they? Because you're
Well,
scaling from around 700 by 500 to a square image.
You've done something, right?
Yeah, that's why I was asking, because some software does a good job. I don't know how well this one does. So that was the reasoning for my question.
Yeah. So I'll quickly go to the one that I figured out what was the issue. So one of the issues that I found was A was the steps per epoch. I should have not calculated it. I should have let the network figure out what that is. And that should be the training size divided by how many epochs you will run it for. Also, the batch size for me was too high. I reduced it to 32. And I trained.
George?
Yep.
Just one quick, so this might be part of the problem. I don't know, it'd be interesting to see, but I was looking at the code, the actual GitHub code for it. I think pre-process input, if you use that, it's going to rescale. It's basically going to divide by 255, right? And rescale the images. But you've already done that in your image data generator. So you're actually doing it twice, which is probably affecting some of the performance.
Got it.
So
that's what I noticed as well. Let's go to version 4.6, where I dropped that pre-processing step, the same setup. Remove this pre-processing step, find the last layer of MobileNet and use that as my output and build on top of that. When I do that and I train for 25 epochs, I'm getting some decent numbers. I'm getting 60, 64, 63. I'm getting better than 40-something% that I was before. So this is, I'm moving in the right direction, basically. So you're saying it's dividing twice. Is that what you're saying, David? By 255?
Yeah, so if you're using the image data generator to do the scaling, but then you were calling the preprocessor from ImageNet, it also does that scaling. So
I'm sure it does other things as well on top of scaling, right?
It doesn't seem to do much else, but
yeah. Then instead of 25 epochs, I said, okay, let me run it for more. And I started this before the meetup. Let's see where it is now. 66, 65, 76 epochs. It's around 66% training accuracy. So I'm not quite there. Yeah. Then I used another model. Instead of MobileNet, I used EfficientNet, but I think I have the same issue here with that rescale and image processing that I need to take a look at, because that is also impacting my training accuracy. That one has way more parameters out of the box as well. For that, I had to install what is called TF Nightly, which is a development version of TensorFlow, because it's not available on the regular TensorFlow 2.2. I want to make sure, that I don't go too far. I think I already went too far. But Robert, David, do you want to maybe share with us from your perspective what you saw and some lessons learned? And I think we have some slides here about that.
You want to go first, Robert, or?
I don't know. I feel like, so I took a totally different tack, basically starting with what George's basic model was, and then making it worse and worse, more investigating the inner workings of TensorFlow. So I think maybe it'd be better. I can share that notebook and you all can go through it, but maybe if David wants to present what he has done now, that would be more in line with what we've already seen.
Sure. So let's look at that slide, George. So I used what's called EfficientNet, excuse me. And George mentioned that he used it in the last thing. It has different versions based on the size of it, number of parameters. And this is just a plot of it compared to other things on ImageNet accuracy. And what I chose is I used the B4 version. It's not that large and it's extremely accurate. on ImageNet. It's I think it's a very neat network to try. So, George, maybe I can just share my screen out and go through my Kaggle. I mean, through my Colab real fast.
Yeah, go for it.
I'm disabled, so host disabled attendee screen sharing. You might have to make me a co-host.
How about now?
Looks good. Okay. All right. Can everybody see my screen?
Yes.
Okay. So very similar to what George did. I went in here, and this is using the data from Kaggle. One thing I'm going to use is right here. It's called Tensorflow Hub. It's an additional package from TensorFlow where a lot of models are uploaded. They're great for doing the transfer learning. So you could take the approach where there are some models built into Keras, and that's what George was using when he used the Keras applications. But you can go to the hub and get a lot of these models, and there's many more in the TensorFlow Hub available to you, and there's a lot of different kind of things. So I'm going to use, as he said, I'm going to use Kaggle just to pull down the files. I'm going to unzip them here, and I'm going to do some image processing on those files to prepare them. I use a very similar type of approach. Maybe some of my exact augmentations were slightly different. I used both the horizontal and the vertical flips. I didn't do any horizontal shifts or anything like that, but this worked pretty well for me. I also created a validation split out of the training data by using this word, and what that does is the image data generators going to set aside 20% of the data in a random fashion. It's going to shuffle everything and randomly set aside 20% for validation as a validation set.
Nice.
And I'm going to flow both for the validation generator and training generator from the same directories from the training content. The model I'm using is EfficientNet B4, and it has a requirement for image size of 380 by 380. Each one of those models is different. They'll change size depending on. The B7 that George uses at the end is 600 by 600 pixels. It's the largest of them. So not only do you have more parameters, also the image size changes with those models. That's another thing to keep in mind. How do I know which, if I'm doing training or validation, I just use this subset, and the image data generator knows which one of those splits I want to get. For the training, I'm going to shuffle every batch, and for validation, there's no reason to shuffle, so I'll keep it the same. And here you can see how it divided them up. Took those 6,000 something and divided it into a training and a test set, each with the 5 classes that it found. All right, so here's a difference in how I'm using the hub. You can pull from the hub a classification model, which would be equivalent to what George was doing with the top included, or you can pull what's called a feature vector module, which is basically the no top solution. Here I'm going to bring it in as a Keras layer, and I'm going to set trainable equals false, very similar to what George did. And then I'm going to put my dense layers on here. The optimism, I'm going to compile it and use Atom, the same loss metrics and the same, this is just a shorthand for accuracy. And now you can see where I printed out my summary. The Keras layer is just represented as one layer by itself with this output shape. It's gone through max pooling at the end and come out with this shape. And that's going to lead to I've got 18,000 total parameters in this B4, EfficientNet B4, and plus my dense layers put on top. But I'm only allowing about 1 million to be trained. So that's important to look at. Then again, I was just checking, looking at all the layers to see what's trainable. Basically, every layer is trainable except for that Keras layer, which is my EfficientNet feature vector. I'm going to start doing my training with my generator. I'm just going to train for 50 epochs. I'm going to save my best results in my model here. And
I'm going to use that validation generator to look at my validations. So I trained for 50, and you can see by the end, I'm about 87% accuracy on my training set. The validation set is about 80%. So I've got a little bit of overfitting going on. That's better represented here. You can see it starting to diverge. It actually was still improving on the training set at 50 epochs, so it probably would have gotten worse as far as the overfitting. But I tried to adjust some of that with the data augmentation. I'm going to load back in my best set of weights when I saved my model out. This is the name of the file that I saved them to. So I'm going to load that back into my model so that I know I have the best version of my model. And then I'm going to do a test generator on those test images that were in there. The only thing I'm doing no augmentation on my test at this point. I'm just going to scale them, and I'm not going to shuffle them, which is really important. Otherwise, when you submit, your things will be out of order. And the other thing that's important, because I don't have labels or classes, I can use this class mode equals none, and that tells it basically that I don't have any. This is just for testing. And I'm not going to train on these test data. I'm only going to predict what the classes are that go for it. So here I do my predictions. I save them into file called predictions. I'm going to go through and take each of these predictions are actually probabilities for the 5 classes. I'm going to look in there, and I'm going to use this NumPy utility called argmax, and I'm going to pick out the best one, what I think is the best one in that range, or the highest probability, right? And I'm just going to use this index of labels that we had to change the numbers from the 0 through 4 into the actual category names. And I'm going to create a submission file based on the sample submission file that George showed much earlier in this Kaggle thing. And I'm going to just print it out to see what it looked like. Here's what it looks like initially as a sample. And these are my actual values that are going in there. So you can see it, it's changing the categories and putting my actual predictions. And just for verification, there's the 3774 that we talked about earlier. And then I'm going to use the Kaggle command line API to submit it. And here's how I'm doing that. And you can put a message in there that it'll save so you kind of know which one this was I submitted. So I'm just submitting this back to the competition on Kaggle directly. And if I go look over there, it actually did fairly well. Here's my most recent submission. This is the one that I just did. The public score, they have 2 test databases out there that they'll run it against. And the public score was 79, 801, and the private score was 83%. And I can't remember exactly how they do that differently, because they're taking your submission and calculating that. But anyway, regardless, let's not get caught up on that too much on the Kaggle competition side. But 83% is pretty good. The actual winner of the competition about a year ago scored a 93. So I'm a little behind them, but not bad, right? For a very small effort. I did also apply the same type of technique to a TensorFlow data sets instead of using the Kaggle data. If you have any interest in this, we can go through briefly, but instead of pulling from Kaggle, I'm using a TensorFlow data set, TFDS. And I think that Lawrence went through this a little bit during the class. But the idea is you can pull in the data here, specify the splits. And as we mentioned earlier, the TensorFlow data set has the splits already made for you, and there's a training, validation, and test split. So I'm pulling all those into data set objects. And then I will go and process it a little bit differently. I'm not going to use a image data generator to do this. I'm going to do it all with the data sets. This is pretty advanced maybe, but if you haven't seen the data and deployment course yet, you might not have been introduced to some of these. But I'm going to, for instance, in the training data set, I'm going to actually normalize the image, which
means I'm going to resize it to the efficient at B7 in this case size it requires. I'm going to convert it to floats and divide by 255, so all the image values are between 0 and 1. I'm not going to do any augmentation in this case. I just was trying to get this going. I can shuffle my data set, batch it up, and make a repeatable data set that so the next epoch it'll repeat it. And I can do some things to speed things up, prefetching and stuff. I'm going to do the same thing with validation, except for I'm not going to shuffle. There's no reason to shuffle it. And I'll do the same thing with the test set. No augmentation.
What we were doing in the time series part, David.
Yeah, I used some of that, right?
Yeah.
So I'll skip by some of this, but as I mentioned, I used the bigger network, the B7 network with the larger images. And again, I'm just going to use it as a Keras layer, as a hub, make it false, and I'm going to add my little dense network on top of it and predict for my 5 classes. Same settings as before. The model now is a little bit bigger. It's 3 million parameters instead of just 1 million. And I'm going to go through and train this for 100 epochs this time with my validation. I do need to declare when you're using a data set like this that's repeated, it effectively never ends. So you do actually have to declare the steps per epoch. Whereas with image data generator, we didn't have to do it. It automatically calculates how many steps it needs to do.
Interesting.
So there's a slight difference when you're using a data set like this, a TensorFlow data set. So I trained it for 100 epochs. As you imagine, it's probably going to overfit, but on the training data, I got 95% accuracy by 100 epochs. And on the validation data, I'm doing pretty well. I'm 83%, which is pretty good, but it is overfitting, obviously. You can see that here. It just takes off probably after about 20 epochs. And then the test set, I just ran it against the test set, and it was very similar to the validation set. Actually got 83% again, which is pretty good. So
nice. I like that the hub is much cleaner approach than what I was using. So I might actually go with the hub version instead of downloading the model and freezing the layers.
All the mobile net models are there, so you would have no problem using the same models and comparing them and everything.
Yeah. What is this very last output? Is that from model.evaluate that you're getting? This baseline additional dense layer, the very last output.
Oh, down here, that's text. That's some of my comments when I was running things and trying out different things.
Okay.
This is my attempt at hyper tuning.
Nice.
the poor man's version. Yeah, I was just tracking my results. You did it in a nice way by creating a new model every time and tracking your results.
Yeah, but my notebook is endless now. I like your.
Yeah, you have a very long notebook.
A much cleaner version of it. Cool. Any questions for David? Really good approach and really good numbers.
Yeah, could you share these 2 notebooks?
I plan to share them out. Yeah, I wanted to clean them up a little bit for you guys, and then I'll put them out on GitHub.
Right. Yeah, because I've never used this pulling from the hub and reusing the model.
Yeah,
doing things very inefficiently.
That's the whole purpose of this coding exercise. We look at others, we look at the entire community, and we get lessons learned, and we learn from each other.
Yeah, thank you.
Can I ask a question?
Go for it.
Yeah. In the model net, there is a input of 225, 225. Can we use, for example, my images are 336, 336. So can we make our model to that required images?
Sorry, Salman, I couldn't quite understand. Are you asking about the input size?
Yeah, input size.
Ah, right. So I typically try to match the model's standard input size to the type of data we have. But a lot of times you can't quite do that. So you're not, at least with these models, you're not required to exactly match it. So I could change this. I probably won't get quite as good of results. If you think about the fact that we're trying to use the transfer learning from a model that trained on a certain size of image. So when it's looking for features in those images, it probably has some tendency to look for features of a certain size as well. That may not always be the case. It may work fine for different size images. The other danger you run into that we didn't talk about too much is that we're using image data generators flow from directory, and not everybody does a real good job of doing resizes. The next version, I think, of TensorFlow is going to have something called Smart Resize that does a better job of not messing up aspect ratios when it does the resizing. So that's another area where it's nice to have a model that requires an image size close to what your actual data set is made up of. Does that make sense?
Yeah, totally. Thanks.
Okay.
David, hypothetically, let's presume that you were a shallow person and that you're 87% and you actually wanted to compete to get 94% or whatever it was. And I noticed you also tried, you mentioned you tried some hyper-parameter tuning and all, but what would your moves be? Where would you focus if you were going to try to, improve those numbers? What next would you do?
So can you still see my screen here?
I can.
So I'll often put some of my ideas up here, and they're aimed sort of like that. I'm not sure I would quantify myself as a shallow person, maybe just interested.
That was the hypothetical, David.
Okay.
You're clearly not interested in competition.
No, not at all.
The higher, it's the higher goals here that you're focused on.
Yeah. So I've already put in some of these, like the zoom, but I might play with dropout. That overfitting is a major issue that I see to the model right now for getting a better score. I think that we're overfitting the training data, and we're not able to generalize to the test set as well, right? So I would first look into things where I could eliminate some of the overfitting. I might apply more dropout. I might try
L2 or something like that, or
say it again.
L2.
Yeah, you could try some regularization approaches. That's right. That'll also help with overfitting. That's another great one. There's a lot more image augmentation libraries out there than what's just available in our data generator. Mm-hmm. So that would be another area I would look at. I mean, you can do Gaussian blurring and do a lot of things that kind of simulate what you might. It's always good to look at the test data, to look at the images and see what, is there something really different about them from what your training data looks like? And you can augment your training data to try to match it better.
These would all be things you'd be doing to your top part of your model, the trainable part of your model, and the rest of it all stays the same, right? The untrainable part.
Yeah, so I would be first looking at, how can I make my data set that I'm training on bigger and more general, right? Okay. So that would be the first thing, and then I might look at the model some. There may be changes we can make to the model to increase. There's another big thing here, which is that they gave us, I can't remember the term, was it 12,000 or something extra images?
Yeah.
That we haven't used at all. Now they're not labeled.
No.
So there's a couple of approaches that I've seen to that kind of thing when you have that. One is to use what's called I don't think we've been through any of this, but it's called an autoencoder. And basically you make your model so that it reduces, basically you have the model that you have that pulls out features in a convolutional layer at the end. And then you start to do what's called upsampling instead of max pooling. and you increase the size back to the original size of your input image. And then in your model.fit, you're comparing your samples going in, your X or whatever, usually in your model, right? You usually have an X and a Y, where the Y's are the labels. Your X is your input image. Your Y, which is the label that you're trying to match, is also your input image. So you're trying to do a pixel by pixel reproduction. So what that does is it forces your model to learn the features of the image, image features, right? And it's trying to reproduce the image on the end to look like it did at the start. Yeah, so if you look up autoencoders for images, you'll find out how they do this. But the idea is that I've got an incoming image and I've got an outgoing label, but my outgoing label is the same image.
Mm-hmm.
So basically I'm trying to do a pixel by pixel comparison in it. I'm basically using a model, what they call the encoder part of the model is the same as what I'm going to later on apply to do classification, right? But I'm going to do that model down to the very last convolutionary layer. And then I'm going to build it up on the other side to get back to the image that's the same size. So I'm trying to learn features, right? Have it learn features on my extra images that are unlabeled. And then I'll take that model and basically in a transfer learning style, I'll then put a dense, layers on the bottom and use it for classifying my training data. And the hope is that I've learned a lot from those extra images in terms of extracting features. So that's one approach that they might use to take in those extra images and do something with them. The other way that I've seen people do this is you can train your model just like we did and get your best model on the training data, right? And if you recall, when we do our classification, we get probabilities for each class, right?
Yep.
So then they would take this trained model that you've built and they would run it against the extra images that aren't labeled,
Mm-hmm.
right? And they would look at the probabilities for all the classes that are coming out. And they might say, well, the ones that it's 90% sure it's got the right class, I'm going to take those as being true.
Mm-hmm.
And I'm going to build another training data set with those labels that I've just predicted. And now I'm going to retrain my model on the original training set, as well as this new training set with the model, with the extra images that I'm sure I've predicted right.
So you're using your best model to annotate unlabeled data and enlarging the regional training pool that you had.
Yes.
You have to be very sure that you're not overfitting.
Absolutely.
If we're doing that.
Yeah.
Could you talk about the cross-validation piece that you're interested in? So first of all, does TensorFlow provide calls for cross-validation?
No, it's one of the major complaints of people that it doesn't have this built in.
Yeah.
So you can use sklearn. I don't know if you scikit-learn, if you've ever heard of that. Sklearn is probably the most popular package for it.
Okay.
And it works with any kind of models. It doesn't have to be a deep learning model. But in this case, I'm not sure how much value it would provide. So the idea is that we made a validation set that was 20%, but did we pick a good 20% of the training labels to use as validation? Wouldn't it be better if we divided our training data in 5 and we used all 5 and we just varied which one were the validations? And so what you do is you assess your model on, like, in this case, the K is 5. So like a 5-fold cross-validation to see if your model's, really doing as well as you think it is. It's very useful for small data sets. This one's on the cusp. I'm not sure, I would consider it small enough to get much out of doing cross-validation.
Okay.
It helps. What it ultimately helps you with is to see if your hyper-parameters are good, or if your choice of your architecture for your model is good, and all that kind of thing. So
That's your.
You know, you may think you're not overfitting, or you may think you've got a great model just because of the validation set you chose, right?
Okay.
Is that the first item in your to-do list, David, that you're talking about?
Yeah, the K-fold.
Okay. What is the TTA and the SWA? What is that? Augmentation?
So TTA is even more interesting. It's basically it's called test something augment. What is it called? Something test augmentation. So the idea is that you will actually now, instead of doing one prediction against our test set, and if you recall, we didn't do any augmentation of the images in the test set, right?
Yeah.
And we just predicted one time. So what they will do is we'll actually do some augmentation, a slight augmentation against our test set. And we'll do that like, I don't know, 10, 20 times. And we're going to do an averaging to get the results.
Test augmentation. Okay.
So the idea is, it creates a little bit more robust predictability, right?
Is it similar to what you said before about using your best model to be an annotator for your test data?
Sort of. I mean, it's a different approach because you're not going to retrain on those test labels, right? You're just saying, okay, it's almost like, you know, you take the same image and you create 10 slightly different versions of it. And if your model, you know, 6 times says it's class B, and the other times it says it's class A, C, or D, well, the 6 times it's class B is probably the right choice.
Got it.
Whereas if you just run it once against it, you might have picked A. If that just happened to be the wrong one, right? So that is, it improves your predictions. SWA is a different type of loss function. Sorry, a different, I'm wrong, sorry. It's a different optimizer.
Oh, I see.
And the idea is that sometimes if you imagine you're descending in the gradients, right? And the minimum is sort of like you get down and there's a large, they visualize it as like you've come to a big pond at the bottom of the mountains, right? But somewhere in that middle is really where you want to get. And it's just very slightly going down into the middle, right? Well, they say most optimizers are just going to go along the shoreline and not really change, like the loss is not really going to change. And what this does is some kind of averaging to be able to get you to the middle. It's a different. I've played with it a couple times and haven't gotten much results with it, so I just put it on there. Something that might benefit. I don't know.
Cool.
Well, you know,
quick question to follow up, if I may. How was the
ahead.
data split into training and validation? I think you mentioned 20%.
When I did it, yes. When I did it with the image data generator, I did the 20% for validation, 80% training.
So which 20% were chosen for, say, the validation?
It's random.
Random for each class or in the totality?
In the totality, yep.
So it's possible that, let's say, for some of the classes that may not be represented, it was even fewer than 20%.
Absolutely, and that's another good reason to do like a K-fold cross-validation, or you could hand do it.
By class.
Yeah, and that's where I think the TensorFlow data set is probably a better validation set to use because they probably have done that. I haven't researched it. I imagine they've got a good representative.
So the other question I have is, when you were doing the exploration, did you try to train the network only on a healthy class as well as one of the disease classes to see whether the data within each class is homogeneous or whether there are some true outliers or there is some egregious mislabeling?
I didn't, and one of the reasons I didn't is I don't know if I have it in here. It might be in my other, it's probably in one of my other things. So one of the things I do a lot of times when there's a class imbalance is I use something called a focal loss instead of just your regular. And what that does is it punishes when for the classes where you don't have as many examples, right? If it gets those wrong, it actually increases the loss more. Basically, it's punishing you. So if you're getting the class that has 90% of the values right, you know, it doesn't reward you much for that, right? I mean, that's great, but that's easy. If you're missing the class, the 10% of the labels, right, that are hard to predict, it's going to punish for that, so that the model does a better job on those less frequently occurring classes. It makes, you know, to compensate for the class imbalance.
I think it makes you focus on those examples where the errors are the largest, right? From what I recall.
Yeah, essentially.
Okay.
Yeah.
All right. So you haven't tried to see whether, say, how the network would perform on two classes, like two pairs.
Right. No, I haven't tried that.
That's fine. Thank you. Appreciate it.
Cool. Any other questions?
Well, I just noticed that there's one thing that's not on your list, and that someone mentioned it last time. It was like something that apparently is very effective in winning the Kaggle competitions, and that would be to do an ensemble where you might create a random forest and then ensemble it with your neural network or your deep learning model. So how about that?
Yeah, so in this case, with this type of data, I would not use an ensemble of a classic machine learning and a deep network. But what you might try is an ensemble of different deep learning networks. So maybe MobileNet, EfficientNet, or ResNet or something, you know, several of those, and ensemble them together.
Can you even do a random forest on this kind of stuff? I don't really know what that is, so you know.
No.
I mean, does a decision tree model apply to this kind of data?
No. This is image. No. This is not structured data.
Okay. All right.
But it's certainly not impossible to attempt to implement it, but it won't work well.
This just doesn't make sense.
Yeah.
Like what the definition of random forest is, because with the definition of random forest is like you basically you're basically like backing like randomly backing like together like a lot of like random decision trees,
Right.
And of course like once you have like this is just speaking from my intuition, like if you just have like thousands of pixels within each image, and then like you multiply it out by like potentially like tens of thousands, like if not millions of like images, and like that like I don't know how conceptually that.
I mean, with the naive implementation of it, you'd be basically randomly selecting pixels from the image and using them to build each of the trees.
It would be overwhelming.
Yeah.
Yeah, exactly.
So Martin, back to your ensemble thing. The other one reason that I wouldn't necessarily use that, you're right that you probably could ensemble a bunch of neural nets and maybe get better results, or deep learning networks. It's resource intensive, right? So I mean, you're going to have to run for a long time with a lot of horsepower. So that's one reason I have this Colab and it's very nice, but it's not that huge. And the second reason is you're probably, you know, if you think about the original use case for this, you're probably not going to deploy an ensemble model out onto someone's cell phone. Whereas these kind of models, you can pretty easily, you know, with TensorFlow Lite, you can convert these models into TensorFlow Lite models and deploy them out to a device like a cell phone.
Yeah, but the model could be scored on a cell phone tower, right? You could deploy it on the edge. It doesn't have to be scored on a cell phone. It could be scored on a cell phone tower. You may have a server connected to a cell phone tower. So.
Oh yeah, my understanding is these farmers in the field may not even have connectivity when they're using, right? They're taking an image. They're not uploading those images necessarily to anywhere to be there. It's all done on the device.
Yeah. That's what I think.
Yeah, farm connectivity is a problem even in United States. So
Yeah.
Especially in the United States.
Oh, especially, I wouldn't say that.
In my area, for sure.
Could be. Yeah.
David, do you mind making me a host? I have 2 more slides and I think we're gonna wrap up here. Thank you.
Yeah.
So these are the slides that we talked about, the different models and their number of parameters and what is their top 1 accuracy on ImageNet. There's another website that a lot of people use. It's called Papers with Code, and there you can see what is called the state of the art. So for different tasks, for example, image classification on the ImageNet dataset, you would see a timeline of different algorithms and which one was the state of the art for each year or each month on this dataset. And you'd see now this Fire Next of Fire Resolution Next. It's actually in the family of the Efficient Net. That one has close to 500 million parameters, so I don't think we have any luck running that anywhere on a mobile device. And then you see different variations of that and their training and top 1 and top 5 accuracy. So yeah, we went through this through our all hands-on session. I just included some screenshots here, what I changed from one version to the other, the issue that I had with preprocessing input, and after removing it. Yeah, I also had a to-do list like you, David, include like callbacks, load only the base one from a checkpoint, maybe introduce a different side of the input, try different transfer learning models like MobileNet and other ones I tried 2 so far. The last one that I wanted to try is something called TF Explain, and I'll talk to that in a second. And we have some notes here from David as well. And TF Explain is an approach, is a library, takes us a little bit closer to explainability in deep learning. As you know, that's a really hard concept. But my goal was, for the classes, for this classification problem, can we really tell what the model is looking at on the leaves? Is it focused on the specific parts that we as humans focus, or is it focused on the shape of the leaf, or is it focused on the light, on the contrast, and so forth? So this TF Explain has 5 different modes, or what they call methods, and one of them that I'd be interested in exploring is called grad cam, or class activation maps, where given a model, you can do this during training, also during test, you can kind of tell where the model is looking at and why where is it tending to when it's classifying an image. I haven't played with it yet. I found it recently this week, so it seems promising and it's popular online, I think. Cool. With that said, I just briefly want to mention that next week I'll put together a corpus of this very famous TV show with the Big Bang Theory. We'll have the corpus in text. We'll also have the audio and the video. I know that YouTube has a lot of copyright issues, so I'm trying to be very careful and very respectful of that. Of how can we do that as a team. Plan B is maybe I can host it somewhere online and we do this individually, but my vision, my goal was for us to listen to something or look at something, and we'll have either an annotation tool, which I'm exploring, or maybe as simple as a spreadsheet, and we identify different users and we can classify each one of us what we think from each sentence. Is this a happy sentence, joy, anger, neutral, sadness, and so forth. There's 6 or 7 categories that we'll see. And if we do that as a group for the entire set, we can use that later on to see if is text enough to detect emotion, or do you actually need audio and video, which in many cases, as you know, as humans do need. And the NLP one is coming up with friends. That's just based on text, no audio or video there. The unstructured data set is coming up as well on credit card, close to 250,000 transactions, and I think a few hundred fraudulent cases. So it's a very highly imbalanced data set in the time series prediction. That's all I have. Those slides are available on the meetup. Thank you again. I know this is probably our longest session, but I hope you find it interesting and exciting, and hope you can join us in our next hands-on session where we will be annotating this data set, and as well as in the future ones. Great. With that said, have a great evening, have a great weekend, and thank you everyone for sticking with us so far.
All right. It was great. Thank you, guys.
Thank you.
Yeah, thank
you,
you.
everyone.
Thank you. Very useful.